Hello everyone, welcome to the Linear Algebra 2 problem solving session 6. Today we will solve the questions from the practice problems for quiz 6. First question is, suppose that V is finite dimensional vector space and T is linear operator on V. Show that if kernel T is equal to kernel T square, then kernel T is equal to kernel T to the m. Now, easy side is kernel T is under kernel T to the m. This was the easier case. To show this, if we take V in kernel T, this implies that T of V is equal to 0, right? Let's look at T to the m V is equal to T to the m minus 1 T V, and we know that this one is equal to 0, so this is equal to 0. So V is in the kernel T to the m. For this side, we don't even need to our assumption kernel T is equal to kernel T square. Now let's show the kernel T to the m is under kernel T. Now I want to do the induction to show this step. Like first case, when m is equal to 2, right? So this m is equal to 2. This is okay because of our assumption. In the beginning of the question gives us kernel T is equal to kernel T square. Now, second step of induction, we need to assume that kernel T to the m minus 1 is equal to kernel of T. Now, let's say kernel T to the m minus 1 is under kernel T. We need to show this one. Now, let's take V in kernel T to the m, right? So, T to the m V will be equal to 0, right? So let's look at, we can write this one as T to the m minus 1 TV, right? So TV is under, TV is in the kernel of T to the m minus 1, and we know that this is equal to kernel of T, right? So T of TV is equal to 0, right? So this implies that V is in the kernel T square. So because of our assumption, we know that this one is equal to kernel T. So this gives us V is in the kernel T. So kernel T to the m minus 1 is under kernel T. So this completes the proof. Second question is, let A be the 4x4 matrix over F2 whose entries are all ones. Find the order form G of A and invertible matrix P such that A is equal to P times J times P inverse. Now, to find this, first we need to find the characteristic polynomial of A. And A is the matrix whose entries are 1, 1, 1, 1, 1, right? All the entries are 1s. So, and if we try to find the characteristic polynomial determinant xi minus I, we will show that characteristic polynomial EAX will be equal to, you can do this as an exercise, will be equal to x to the 4. Now we need to find the minimal polynomial of this matrix. Now, minimal polynomial can be equal to x square, x cube, or x to the 4, right? Now, if the minimal polynomial is equal to 0 from Cayley-Hamilton, a must be equal to 0, but a is not equal to 0, so minimal polynomial is not x. So this case is gone. Let's look at the x square. Let's write a square. A square, if you do the computation, you will see that a square is equal to 0. So minimal polynomial of a will be equal to x square. So, and also we know that the power of x, which is 2, will be equal to the largest integer in the partition corresponding to Jordan form. So let's try to write the Jordan form. J will be equal to, now since our eigenvalue, there is only one eigenvalue, which is 0, right? So in the diagonal we will have 0, 0, 0, right? So below the diagonal we will have again zeros. Now above the diagonal we can have we will have blocks, right? And the maximum block, largest block will be dimension must be 2 by 2 matrix. So it can be something like this, right? We can put 1. This will be the block 2 by 2 block, right? Then other parts can be 1 by 1 blocks. So this part will be 0, 0, 0. So this is one case, and the other case, again we have the zeros in the diagonal. Again, first one can be 2 by 2 block, and the second one again will be 2 by 2 block, right? So largest block still 2 by 2. Largest block still in the form 2 by 2. So our Jordan form, one of these ones. Let's look at the ranks. Rank A is equal to 1, right? And rank J, let's say this J, rank J is again 1, and rank J prime is 2. So our correct Jordan, since these two have the same rank, our Jordan form must be this one. This cannot be Jordan form. So now we have the Jordan form. Our Jordan form is 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? This is our Jordan form. Now we need to find the matrix P, and we know that AP is equal to PJ, right? And we can write P as the vector V1, V2, V3, V4, and again V will be V1, V2, V3, V4 times J. So this gives us, because of this one, we will have that A times V1, A times V2, A times V3, A times V4 will be equal to 0, V1, 0, 0. So we have AV1 will be equal to 0, AV2 will be equal to V1, AV3 will be equal to 0 and AV4 will be equal to 0. Now we need to choose V1, V2, V3 and V4. Let's try to find this one. AV1 is equal to this system. AV1 is equal to 0. A was 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 must be equal to 0, 0, 0. So if we add row 1 to row 2, row 1 to row 3 and row 1 to row 4, we will have 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. We must have this matrix. So now this one, the x1 entry, x2 entry, x3, x4, right? So x1 is equal to minus x2 minus x3 minus x4. So general form of the solution of this system will be x4, x3, x2 and minus x2 minus x3 minus x4. Now let's try to solve now. Let's say we don't know right now what is the correct one, but let's say V1 is of this form for some x2, x3, x4. Let's try to solve the next thing. AV2 is equal to V1, right? So we will have 1, 1, 1. So we don't need to minus 1 is equal to 1 in F2, right? So these are x2 plus x3 plus x4. 1, 1, 1, x2 plus x3 plus x4, 1, 1, 1, 1, x2, 1, 1, 1, 1, x3, 1, 1, 1, 1, x4, right? Let's again add row 1 to row 2, row 1 to row 3, and row 1 to row 4. So we will have 1, 1, 1, 1, 1, 0, 0, 0, 0, and we will have x2 plus x2 is 0, 2x2 is 0, so we will have x3 plus x4, and we will have 0, 0, 0, again x3 plus x3, 2x3 which is 0, x2 plus x4, 0, 0, 0, 0, then I will have x2 plus x3. Now we have this system, but this system must have the solution, right? We know that AB2 is equal to B1, so this one must be equal to 0. So x3 plus x4 is equal to x2 plus x4 plus x2 plus x3. These are 0, right? So if x3 okay, it can be everything will be 0, but then this one again will be 0. Sorry. Here we have still x2 plus x3 plus x4. Now from here we can see that they can be all 0 or they can be all 1s, right? But 0 will be this trivial solution, so we can have x2 is equal to x3 is equal to x4, which is 1, and here x2 plus x3 plus x4, 1 plus 1 plus 1 is equal to 3, right? So V1 will be equal to 1, 1, 1, 1. Now we need to find V2. Now this is easier because we know that. Now we need to solve this one. 1, 1, 1, 1, and 1. The other entries are zeros. Now we need to solve this one. This x3, x4, x2, x1 was belong to b1. Now we will have again x1, x2, x3, x4. Now let's say, so from here x1 will be equal to 1 minus x2 minus x3 minus x4. Let us choose x2, x3, x4 that is equal to 0. So x1 will be 1. So v2 will be 1, 0, 0, 0. Now we also need to choose v3 and v4. v3 and v4 still in this form, right? So for v3, let's say these are primes. And I will return to this case again. So actually this is not only v1, v3 and v4 also in this form. For x3, for v3, I choose x3 and here x3 and x4 is equal to 0 and x2 1. So I will have the vector 1, 1, 0, 0, right? So for vector 4, I choose x2 and x4 is 0 and x3 is 1. So I will have 1, 0, 1, 0 vector. So I find the 4 vectors and I need 4. So now I can write the Rp. P will be equal to, now v1 was 1, 1, 1, 1. v2 was 1, 0, 0, 0. v3 is 1, 1, 0, 0. And v4 is 1, 0, 1, 0. And this exercise for you, P inverse will be 0, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1. This is exercise for you. Then A will be equal to 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0 times this was P. Our Jordan form is 0, 0, 0, 0, 0, 1. Okay, this is our Jordan form times P inverse. Now, question 3 is 5 all 5 by 5 nilpotent Jordan matrices up to an ordering of Jordan blocks. How many of them are there? Now, characteristic polynomials of these matrices are x to the n. Now, so minimal polynomials will be, can be x squared, x cubed, x to the 4 and x to the 5, right? And eigenvalues are, eigenvalue is 0, right? Now we need to write this Jordan form. For characteristic polynomial is equal to x. Let's look at this case. If characteristic polynomial is equal to x, if the characteristic polynomial is equal to x, we can write, this means that like this is x to the 1, right? So maximal blocks will be 1 by 1. So since the maximal block is 1 by 1, all blocks must be 1 by 1. So this is equal to 0, 0, 0, 0, right? 0 matrix. So again, you can also see that x is equal to 0, right? Now, this is not the characteristic polynomial, this is minimal polynomial. Let's say mx is equal to, x squared, right? Now, maximum block will be in the size of 2 by 2, right? So we can have, again, in the diagonal, we will have 5 zeros, right? So we can have 1, 1 here, right? So we will have 1 block of the size 2 by 2 and 3 block of the size 1 by 1. Also we have one more case. We can have 1 block of size 2 and second block of size 2 by 2 and the third one size 1 by 1, right? This is the size 1 by 1. This is 2 by 2, 2 by 2 and 1 by 1, and still maximum size is 2 by 2. Now let's look at if the minimal polynomial is x cubed. If minimal polynomial is x cubed, we should have maximal size of the blocks will be 3 by 3, right? So 0, 0, 0, 0. We need to have 1 block at the size 3 by 3. Then this can be 1 by 1. This is one case. This can be, the other blocks can be 1 by 1. But also we have one more case, which is, okay, first block is 3 by 3. We cannot have second block at the size 3 by 3, but we can have second block at the size 2 by 2, right? Still maximal size is 3 by 3. If the minimal polynomial is at the size x to the 4, we need to have one block size 4 by 4, right? Since this minimal polynomial is x to the 4. So this is the block size 4 by 4. And we have just one space, which is 4, 1 by 1 block. And if minimal polynomial is x to 5, we will have, so maximal block will be in size 1 by 1, right? So 5 by 5, and our matrices are 5 by 5, so we will have only one block at size 5 by 5. This is the block size 5 by 5. So how many of them? We have 1, 2, 3, 4, 5, 6, 7. So we will have 7 matrices. Question 4 is, find all possible Jordan matrices whose characteristic polynomial is x cubed, x minus 1 to the 4, and whose minimal polynomial is x squared times x minus 1 squared. Now, since the minimal polynomial is x squared times x x minus 1 square. Maximal size of the blocks will be 2 by 2 for eigenvalue 0 and for the eigenvalue 1, right? So first lambda will be equal to 0, right? Let's find the Jordan blocks for lambda is equal to 0, right? So this one must be 3 by 3, right? Because in the characteristic polynomial x cube is, we have x cube, right? So this must be in the 3 by 3. But the maximum size of the Jordan blocks is 2 by 2, right? We have x squared. So we should have 0, 0, 1 should be 2 by 2 blocks. And the third block will be in the size 1 by 1, which is 0. So the second Jordan blocks must be for lambda is equal to 1. So Jordan matrix for lambda is equal to 1 must be 4 by 4, since we have x minus 1 to the 4, right? But inside of this block, maximal size of the block must be 2 by 2, right? We have x minus 1 square in the minimal polynomial. So first one can be, in the diagonal, in this case we will have 1, 1, 1, right? So we can have 1, 1, 1, and we can have the other blocks are size 1 by 1. But we can have also second option. Again, first block can be at the size 2 by 2, and second one can also be at the form 2 by 2, right? 0, 0, 0. Now, so we can have two possible Jordan matrices whose characteristic polynomial is this one, and whose minimal polynomial is this one, which is, it can be of the form J0, J1, or it can be of the form J0, J1 prime. So we have two possible Jordan matrices whose characteristic polynomial is this one and whose minimal polynomial is this one. Question 6. Find the Jordan form J of the matrix A over R. Find an invertible matrix P such that A is equal to P times J times P inverse. Now, this exercise for you. If you try to find the characteristic polynomial of this A, this will be equal to, the term is xi minus I will be equal to x to the 4. This is an easy case. Now, to find the minimal polynomial, we need to look at that candidates for the minimal polynomial. Mean polynomial are x, x squared, x cubed, x to the 4. And if you try, again, this exercise for you, if you try to find these matrices, you will see A is not equal to 0, right? And A squared is not equal to 0. A cube is not equal to 0, but you will find that A to the 4 is equal to 0. So minimum polynomial of A will be equal to x. Now we need to write the Jordan form, Jordan matrix, Jordan form. Let's say Jordan form. J will be equal to, minimal polynomial will be, since only A to the 4 is equal to 0, minimal polynomial will be x to the 4. So maximum size of the Jordan blocks will be 4 by 4, must be, must be 4 by 4. And our Jordan form is 4 by 4. So there will be only just one block. Eigenvalues are 0, 0. And size of the block is 4 by 4. So we will have 1, 1, 1 here. And other entries are 0. Now, this is our Jordan form. Now we need to find the P. Again, we will use the fact that A times P is equal to P times J, and we can see P as the vectors V1, column vectors V1, V2, V3, V4, right? So if we do this multiplication, we will have AV1, AV2, AV3, AV4 will be equal to, this one times this one is 0, this one times this one will be V1, this one times this one will be V2, and this one times this one will be equal to V3. So we need to solve the equalities. AV1 is equal to 0, A times A of V2 will be equal to V1, A of V3 will be equal to V2, and A of V4 will be equal to V3. We need to find this, we need to solve these 4 systems. Let's first solve first one. So now we have, which is AV1 is equal to 0. Let's solve this one. A was 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, and 0, 0, 0, 0. And this one is 0, 0, 0, 0. Now, from this row, we can see that x2 is equal to 0, right? And from this row, we can see that x3 is equal to 0. And again from this row, we can see that x4 is equal to 0. But there is no condition for x1. x1 is arbitrary. So v1 will be equal to 1, 0, 0, 0. I choose 1 as an x1. You can take other things. You can take 2, 2, 0, 0, even like 262, 0, 0, 0. Now, for the second equality is, second system, we need to solve is A, B2 is equal to V1, right? So this one will be equal to, again we have the same matrix A, 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, and we have 1, 0, 0. From here, we can see that, and again, x3 is equal to 0, right? Again, x4 is equal to 0, and here we can see that x2 is equal to 1, and again x1 is arbitrary. x1 is arbitrary. Now choose x1 is equal to 0, then v2 becomes, if x1 is equal to 0, we have 0, 1, 0, 0. Now we need to solve third system. AV3 is equal to 0. We have again the same matrix. V3 is equal to V1, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0. And we will have 0, 1, 0, 0 at the other side. Now, here we can see that, or we can deduce that x2 will be equal to 0, right? From this row. From this row we can see that x3 is equal to 0. And from here we can see that x3 is equal to 1. So x3 is equal to 1 over 2. Again, x1 is arbitrary. Choose again x1 is equal to 0. I'm choosing x1 is equal to 0 for the simplicity. You can choose other values again. So v2 will be equal to 0, 0, 1 over 2, 0. Now we have to choose one more system, which is AV4 is equal to V3. So we will have 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, 0. 0, 0, 1 over 2, 0. Again, as you can see, from here, x2 is equal to 0. From here, x3 is equal to 0. And from here, x4, 3x4 is equal to 1 over 4. So x4 is equal to 1 over 6. And again, choose x1 equal to 0. Then v4 will be equal to 0, 0, 1 over, 0, 0, 0, 1 over 6. So we find all four vectors. Now we can write the matrix P, which is, now v1 was 1, 0, 0. v2 was 0, 1, 0, 0. v3 was 0, 0, 1 over 2, 0. And v4 was this vector 0, 0, 0, 1 over 6. So this is P, and I found the P inverse before, and if you try to find P inverse in this question, you will find that P inverse is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 6. And so RA is equal to 1, 0, 0, 0, 1, 0, 0, 0, 0, 1 over 2, 0, 0, 0, 0, 1 over 6 times Jordan form, which was 0, 0, 0, 0, 1, 1, 1, and the other entries are 0, times this one, 1, 0, 0, 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 6. So, if you try to do this computation, you will see that this multiplication will be equal to A. I will remind you again, please check that your P's and your Jordan forms are true after you solve the question. Question 10 is find Jordan form J of the matrix A over R. Find the invertible matrix P such that A is equal to Pj P inverse. Now again we need to find Jordan form of J. This exercise show that characteristic polynomial of A will be equal to x minus 2 square times x minus 3 square, and minimal polynomial of A will be equal to x minus 2 times x minus 3 square. This is an easy exercise for it. Now, since minimal polynomial f of A is this form, now we can write the Jordan form. Let us first write the Jordan blocks for 2. Jordan block for 2. So, since characteristic polynomial x minus 2 has degree 4 in the characteristic polynomial, Jordan block for Jordan matrix for eigenvalue 2 will be of the form 2 by 2. Now, maximal block in this block will be 1 by 1, right? Since in the minimal polynomial we have x minus 2 to the 1. So we will have 2, 2, and blocks will be 1 by 1. So this is the Jordan form of 2. Now let's find the Jordan form of 3. Now 3 has again degree 2 at the characteristic polynomial x minus 3 square. At the minimal polynomial we have again degree 2, right? So we should have 2 by 2 block in the 2 by 2 matrix. So 2, 2, this must be 1 and this must be 0. So our Jordan, these are 3. We are at eigenvalue 3. So our Jordan matrix will be of the form 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 1, 3, 0, 0, 0. This is our Jordan form. Now we need to find the P. Now we have that A times P, which is, let's write this one as V1, V2, V3, V4, should be equal to V1, V2, V3, V4 times J. So if you compute this equality, we will have AV1, AV2, AV3, AV4 is equal to 2 times V1, 2 times V2, 3 times V3, and V3 plus 3 V4. Now we need to solve the systems. AV1 is equal to TV1, AV2 is equal to 2V2, AV3 is equal to 3V3, and AV4 is equal to V3 plus 3V4. This one implies that A minus 2I times V1 is equal to 0. This implies that A times 2I V2 is equal to 0. This one implies A minus 3I V3 is equal to 0. And this implies that A times 3I V4 is equal to V3. Now we need to solve this first system. Now let's first look at this one, A minus 2I. Both of them are the same. A minus 2I is equal to 0. So A minus 2I, let's solve this one. A minus 2I V1 is equal to 0. So we will have 2, 0, 1, 0 and 2, 0, 3, 0 minus 1, 0, 0, 0, 4, 0, 1, 0, 0, 0, 0. Now, for V1 and V2, we need to solve this system. Now, let's add minus row 1 to row 2 and minus 2 row 1 to row 4. So we will have 2 0 1 0 0 minus one of this one here, 0 0 2 0 0 minus 1 0 0 0 0, and here minus 2 4 0 0 3 0 0. Sorry, it's not 3, minus 4. Now from here we can see that let's say this is x1, x2, x3, x4. X3 is equal to 0. Since if x3 is equal to 0, x1 is equal to 0, and these are again true. So we will have like x2 and x4 are arbitrary. So let's choose for v1, let's choose x2 is equal to 1 and x4 is equal to 0. So v1 will be equal to 0 1 0 0, and for v2 choose x2 equal to 0 and x4 is equal to 1. So we will have v2 0 0 0 1. So we find v1 and v2. So now we need to find v3 and v4. So v3 and v4, for v3 and v4 we need a minus 3i times v3 is equal to 0. First we need to solve this one. So this one will be equal to a minus 3i will be 1 0 1 0 2 minus 1 3 0 minus 1 0 minus 1 0 4 0 1 minus 1 0 0 0 0. Now we need to solve this one. For this one, if I add row 1 to row 3, minus 2 row 1 to row 2 and minus 4 row 1 to row 4. So I will have 1 0 1 0 0. I add this one here, so minus 2 row 1 here. I have 0 minus 1 minus 2 1 0 0. This one becomes 0 0 0 0 0, and this one becomes 0 0 minus 4 plus 1 minus 3 minus 1 0. So if let's say x1 x2 x3 x1. Now choose x3 is equal to 1. Then this one, x2 becomes x2 becomes 1, x1 becomes minus 1, and x4 becomes minus 3. So our v3 will be minus 1 1 1 minus 3. Now we need to solve the system a minus 3i times v4 is equal to v1. So I need to solve this one 0 1 0, and this one 3 0. This is again the same matrix. This one is not this one. 1 minus 1 1 minus 3. If I did the same row operation again here, we will have this one will not change, minus 1. Okay, if I add minus 2 of this one is here, 0, minus 1, 1, 0 minus 2 times minus 1 is 2, 3, and this one will become 0, 0, 0, 0, and this one becomes 0, minus 4, 0, minus 3, minus 1, plus 3, minus 3, okay, sorry, minus 4 times minus 4 is 4, so this will be 1. Now choose x3 is equal to 1, so we will have from here, if this one is equal to 0, x4 will be equal to minus 1. Now from here, if this one is 0, this one becomes minus 3, so x2 becomes minus 3, and here x1 will be equal to minus 1, so v4 will be equal to minus 1, minus 3, 0, minus 1. So, since we find all the vectors, and we can write the p. P will be equal to, now let's look at here, v1 was 0, 1, 0, 0, v2 was 0, 0, 0, 1, and v3 becomes minus 1, 1, 1, minus 3, and v4 was minus 1, minus 3, 0, minus 1. So we can write the inverse of this matrix, which is so the P inverse will be minus 3, 1, minus 4, 0, minus 4, 1, 0, 2, 1, 0, 0, 1, 0, minus 1, 0, minus 1, 0, and A will be equal to 0, 0, minus 1, minus 1, 1, 0, 1, minus 3, 0, 0, 1, 0, 0, 1, minus 3, minus 1, and Jordan form was 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 1, 0, 0, 0, 3 times P inverse minus 3, 1, minus 4, 0, minus 1, 0, 2, 1, 0, 0, 1, 0, minus 1, 0, minus 1, 0. So if you check this multiplication, you will see that this one is equal to A. So this completes the question. Now this is the end of the this problem session. Thank you for listening to me. I am planning to do more problem solving sessions before the exams. See you next time. Bye.